This is 2018 AIME I problem number 11, and here is a view of this problem. We would like to find the smallest positive integer n such that 3 to the n, when written in base 143, has its rightmost two digits equal to 0 and 1. Okay, so let's go ahead and express this. So 3 to the n, let's say, is equal to, in base 143, say it is a number, I don't know. Well, the only thing we know is the last two digits is 0, 1. I don't know, maybe we can say this one is n1, n2, and so on, right? So n3 and blah blah blah, where n1, n2, and n3 are digits in base 143. So this number is written in base 143, but we know exactly how to convert this into base 10, and let's go ahead and do that. So therefore this is equal to 1 times 1 plus 0 times 143 plus n1 times 143 square plus n2 times 143 cubed, and so on. Well, it is clear that, this is 1, this is 0, it vanishes, so 1 plus. Yeah, it's clear that all the remaining terms, starting with this one, has a 143 square in it, so we can factor out the 143 square. What we are left is n1 plus 143 and 2 plus 143 square and 3, and so on. But then, so this is 3 to the n. This implies if we take mod 143 square of both sides, or if you will, what I mean is if you divide 3 to the n by 143 square, this second term, this term here, is perfectly divisible by 143 square, so therefore the remainder would be 1. So this implies 3 to the n is congruent to 1 in mod 143 square, but 143 is just 11 square times 13 square. That's it. So therefore the whole question is asking find minimum and that satisfy this, right? So that's it. So at this stage, we just realized that 11 square and 13 square, they are relatively prime. So 11 square, the greatest common divisor between 11 square and 13 square is 1. It is suggesting that we can split this into a system of equations in the spirit of Chinese remainder theorem. So therefore, we have 3 to the n is congruent to 1 in mod 11 square, and 3 to the n is congruent to 1 in mod 13 square. So this is an equivalent representation of this expression of this single congruence. So we split it into two congruences. So we would like to find the least n that would satisfy both of these congruences simultaneously. Okay, so now we need to do it case by case. So let's first start with the first one. So 3 to the n is congruent to 1 mod 121, and let's start testing different values for n. So 3 to the 1 is congruent to 3 in mod 121, 3 square is 9, 3 cubed 27, 3 to the 4 is 81, 3 to the 5 is 81 times 3 is 243, and nicely 243, well, let's put an equal sign here. 243 is simply equal to 1 plus 2 times 121. Aha. So therefore this suggests that this is congruent to 1 mod 121. So therefore 3 to the 5 satisfies, so n equals 5 works, solves this thing. What else works on that case? Well, because 3 to the 5 k, right? If you check all these expressions, this would be equal to 3 to the 5 to the power k, but 3 to the 5 is simply, oh my, okay, but 3 to the 5 is simply congruent to 1. in mod 121. So therefore this is 1 in mod 121. That's it. So therefore all multiples of 5 are generate and solves this this congruence, and these are the only ones that solve this congruence. Do you see why? Okay, so moving forward, so therefore the n's that satisfy this thing, so this implies that n is equal to 5. So we decided it would be multiples of 5, right? All multiples of 5 satisfied, so 10, 15, 20, and so on. That's pretty decent, right? So let's clearly mark it here, so like that. Okay, so let's go to the second one. The second one is slightly more involved, but not too much. So 3 to the n has to be congruent to 1 in mod 169 as well, which is 13 square. When you test out different powers, you just realize that it doesn't necessarily give a nice result that we got early on here. And that tells us that maybe we need to look more carefully. So in that case, because 169 is just 13 square, a nice idea would be to check what happens to 3 to the n. Let's write that down. Consider, so we want to solve this thing now. We consider what happens to 3 to the n congruent to 1 in mod 13, right? Does that make sense? So therefore we are looking for n values of n that is congruent to 1 in mod 13 square. Hey, if a number, so consider 3 to the n as your number, is congruent to 1 in mod 13 square, do you guys agree that that number will also be congruent to 1 in mod 13 as well, right? Does that make sense? For instance, let's just explain what I mean. So all this means is that 3 to the n is equal to 1 plus, say, q times 13 square. What I claim, so that's a q, is that, hey, that's the same thing as this, 1 plus 9 times. What the heck? What am I doing? I'm lost. Okay, so this is a horrible notation. Okay, so how about t here? Okay, 13 times t times 13. Does that make sense? I just split. Hey, what that means is if I divide 3 to the n by 13, the remainder will still be 1. So therefore, whatever is the solution to this thing with 13 square in mod 13 square must be a multiple of the solution of this one in mod 13. Does that make sense? So therefore let's instead solve this one, which is significantly easier to solve. So we have well, obviously 3 cube is 27 and it solves it, right? So this implies n is equal to 3. Now, so the solution to this guy, obviously. Now, we know that the solution to this one with 13 square in mod 13 square must be a multiple of 3, right? But then exactly which one, right? So that's, it's not sure which one. So one of them, right? So we want to find at least the least solution to this problem, right? So let's write that down. The least n that solves this. When I say this, I mean this expression, because that's why I had this arrow pointing to it. So the least, this equation is a multiple of 3. Okay, now that I know that it has to be a multiple of 3, let's investigate this expression now, like we did earlier, right? So once we understood that it must be a multiple of 5, and so that's how we did it. So it has to be a multiple of 3, but wait, that's simply equal to 3 cubed to the power k, which is just 27 to the power k. Now be careful, that 27, I don't want to write it as 3 cubed. I would be back to where I started. Instead, I will write it as 1 plus 2 times 13 to the power k. And all I need is to investigate this in mod 169. So let's expand this using the binomial theorem. So that's just 1 plus, well, this was k choose 0. So k choose 1 k choose 1 times 1, well, okay, so let's just do it slowly, times 2 times 13 plus k choose 2, 1 to the k minus 2 times 2 times 13 square, and so on. But now I want to calculate this expression in mod 169. In mod 169 in mod 13 square, look at this expression. It has a 13 square in it, so it vanishes. This one vanishes. Every term afterwards will have a... So in mod 13 square, they all disappear. So all that's left is the first two terms, which is 1 plus k times 2 times 13. That's it. And we want this expression here to be congruent to 1 in mod 13 square, or 169. Hey, that's easy to solve. The ones here, they vanish. So we have k times 2 times 13 is congruent to 0 in mod 169, or 13 square. Let's just write it as 13 square. Now, what should I have? So we want this number to be perfectly divisible by 13 square. But so far it has only a single 13, and 13 and 2 are relatively prime. This implies that the least k that satisfies this expression is 13 itself. Does that make sense? Now I can go back, and I realized early on that it was the so k. So the n that satisfies the original thing had to be a multiple of 3 from our earlier analysis. So now we further recognize that k itself is 13. So therefore, the numbers that work in that case, that the solutions to this problem, let's put it in red as well. The solutions to this guy are, well, it is 3 times 13 now. We have a 13 here, and we also know that the 3, right, multiple of 3. So it should be a 39, and so multiples of 39, right? Does that make sense? But now we have our other list, so we want n to be in that range. We want n to be satisfying this as well. So can you tell me what is the value of n that will be both in that? What is the smallest n that will be in this list and in this list? Well, obviously, because 39 and 5 are relatively prime, so therefore, right, so therefore it would be the greatest common divisor of, the least common multiple of these two numbers, which is just the product of those two numbers. And 39 times 5 is simply 195, and that solves this nice problem.